In this problem, we have a snowboarder who goes down a hill and then along a flat surface, and we want to find the person's acceleration on the hill, their acceleration on the flat surface, or in this case, deceleration, and how far along the flat surface they get before they come to a complete stop. We have a lot of information given to us. The mass of the snowboarder is 75 kilograms. The snowboarder starts at 5 meters per second going down the hill. The hill has a 28-degree incline. The length of the hill before it becomes flat is 110 meters. And the coefficient of kinetic friction on the hill is 0.18 and on the flat surface is 0.15. So this is a lot to work with, and it might take a bit to figure it all out, but we'll take it one step at a time. So we'll start with a free body diagram for the first part where he's on the hill. And we know that the hill goes this way and has an angle of 28 degrees. So we'll think about what forces are applied to him. There is gravitational force, force of gravity, which is going to be equal to mg. We'll have the normal force perpendicular to the surface, force normal, and we'll have the force of kinetic friction, which I'll call Fk. Sorry. Okay. So in order to solve this, we're going to have to put them all into perpendicular components. So what I'm going to do is I'm going to break the force of gravity to have one component opposite of the normal force. So that's equal and opposite to the normal force. And then one force opposite to the force of kinetic friction. And assuming we are accelerating down the hill, this will be greater than the force of kinetic friction. So how to figure out what these are is we do a little bit of geometry, and we can discover that this here is 28 degrees, as this is the right angle and this is the right angle. And then we can use our trigonometry to sort these out. So this force, which is actually equal to the force of the normal force, is equal to, will be equal to cosine 28 degrees times our force of gravity. This force will then be a sine. This force, which I'm just going to call F1. F1 is going to be equal to sine 28 degrees times our force of gravity. And we know that the force of kinetic friction is equal to the coefficient of kinetic friction, at this point 0.18, times the normal force. So in order to figure out our net force, which we're expecting to be moving down the hill, we'll take this component here and subtract this component of the kinetic force. So it's the force pointing down the hill minus the force pointing up the hill. So yeah, force net is going to be equal to force pointing down the hill, sine of 28 degrees times our force of gravity, which will be mg, minus the force pointing up the hill, which is mu k f, so if not, that's a normal force, uk fn. So coefficient of kinetic friction times our normal force, which we have over here as being cos 28 degrees times Fg, which is equal to mg, that's the force of gravity, And what we're actually looking for is acceleration. So I'm going to break our net force open to say that this is going to all equal to ma. Now we have mass in each term, so we can cancel those out. And I'll simplify it a bit. Once again, put a back on the left side. A is equal to sine 28 degrees G minus UK is 0.18 cos of 28 degrees times G. So using trigonometry, sine of 28 is equal to 0.47, 0.47 G, which is equal to 9.8 meters per second squared, minus 0.18. Cos of 28 degrees is 0.88, and G is again 9.8 meters per second squared. And if we solve this, we'll get A is equal to 3.05 meters per second squared. So that's quite a bit, and it uses a lot of multiplication and trigonometry and free body diagrams, but that using this method, you can get the acceleration equal to 3.05 meters per second squared. Now, what we want to do next is let's find our velocity at the bottom of the hill, as this is fully related to the acceleration we just found. So to do this, we're going to use the equation where distance is equal to velocity final, which in this case is our v1. So velocity final squared minus our velocity initial squared, which is the 5 meters per second. All this this is the wrong equation. Sorry about that. This is acceleration is equal to velocity final squared minus velocity initial squared divided by 2 times the distance. And if you're curious about how to determine this equation, you can do it with 2 parts. Delta t, change in time, is equal to change in speed over change in distance. And change in time is also equal to change in acceleration over change in speed. So you pair those two and you can solve it for A. What we're going to do next, so we're going to solve this for our for our V1. We have D as 110 meters. We have V0 as 5 meters. And now we have A as 3.05 meters per second squared. So just isolating for D, so it's going to be D is equal to, isolating for V1, say V1 equal to square root of 2D times acceleration minus V0 squared. This is equal to square root of, say, 220 times 3.05 minus Again, V0 is 5, so this is 25. And this gives us a V1 equal to 26.4 meters per second. So we know V1 is now equal to 26.4 meters per second. So I'm going to continue a bit further to the right. See. Just going to move this down and we can continue below with the new information. Now on to our second one. We know A1 now. Again, A1 is equal to 3.05 meters per second squared. We know V1, and we can continue with our second half, which is A2. So we're going to do a free body diagram again. We have our force of gravity pointing down. This time we're on a flat surface, which makes it a lot easier because our normal force is just completely opposing force of gravity. Very nice. We're still moving. We're moving to the right still, as V1 indicates, still to the right. So our force of friction will be opposing it to the left. So here we have our force of kinetic friction, Fk. So Fg is equal to mg. Force normal must also then be equal to mg. And our force of kinetic friction is equal to 4 is equal to mu k Fn, which in this case is equal to 0.15 times Fn, which is mg. And again, we're looking for acceleration. So we can say ma, which is since the force of kinetic friction is the thing that's accelerating us in the leftmost direction, that's equal to ma. So we can cancel out our m's, and our acceleration is equal to 0.15 g, this time in the left direction. So we can say our acceleration is equal to 0.15 times 9.8, which is equal to negative 1.47 meters per second squared. Again, I made a negative because we're accelerating to the left this time. So it's actually a negative force as well. Now we have both of our accelerations, A1 being 3.05 meters per second squared, A2 being negative 1.47 meters per second squared. And all we have to find is this distance. We're going to use the same equation as before. Acceleration is equal to v final squared minus v initial squared over 2 times the distance. So I'm going to write that here. Acceleration is equal to v final squared. Here, v final squared will be this, so 0, minus v initial squared, which is v1, which is again 26.4. Just, this is the initial velocity and the final velocity because the distance is the distance between those 2 points. .4 meters per second. Yep. And I like it squared. And then divided by 2 times the distance. And we don't have d yet. We're looking for d. So we solve for that, and we will get d is equal to negative 26.4 meters per second squared. Sorry, meters per second, but the whole thing is squared. Should be clear on that. The negative actually isn't squared. Sorry again. Divided by 2a, where a is negative 1.47 meters per second squared. And we can solve this, and that'll give us a final distance equal to 237 meters. So I know that was a lot, and it may be a bit confusing at times, and if so, I'm sorry. But you just have to take it one step at a time, do the free body diagrams, and remember your different formulas for acceleration, as that'll be key. Okay. So once again, acceleration 1, 3.05 meters per second squared. Acceleration 2, negative 1.47 meters per second squared. And the final distance before he comes to a stop is 237 meters. Thank you very much.